So, there was an internet problem. So what I've got now... there was an internet problem. So what we got now is I passed the output of the fast averaging, or the fast filter, into a buffer. From the buffer, I'm sending it into so this is this. Yeah. So in fact, what I've done is this, because I needed to sort of offset. What I've actually done is not offset, but change the amplitude. But since it's a DC level thing, it changes the offset as well. It's perfectly fine, I think. So the room in here. The output of the first buffer. Hey, Michael, how you doing? Output of the first buffer to a variable resistor, which is 4.7k, because that's what I had. That's this guy just here. The output of this goes into the positive input of a second operational amplifier. And I don't need all of this stuff. This is overkill. I don't need that. I think I just need 2 operational amplifiers. It's absolutely fine. So second one, you can come in here like that. Oh, wait a minute. Oh yeah. Yeah. That's all good. I don't need the feedback, because I actually intentionally want it to be infinite gain. So just that is enough, and it just is like a volume control. It's like if this is, you wire it up this way so that there's always a 4.7k load on here. And it isn't like it's going to short something out when you rotate the the variable resistor. If it's all the way down here, you get the 0 signal going into here. You push it up and you get the full signal going into here. And like I said, this isn't just an offset, it's actually just changing the amplitude. That is actually fine, I believe. This would be the sensitivity control. So all I want to do is set that to a value where the results what I want. Recap, I've got amplifier reading audio signal from my condenser microphone. It's going into 2 filter circuits, one with a longer time than the other. One's using a 100 microfarad capacitor, the other's using a 10 microfarad capacitor. The fast one, the 10 microfarad capacitor, goes through a buffer circuit, and then its gain, the amplitude is tunable here and goes into the positive input of a second operational amplifier. I've got to hook that up yet. The other one, the longer time filter one, which is used as a baseline, is compared against the fast one. So if there's a transient, the fast one lifts up earlier than the slower one, and so then it will detect that difference, and then by adjusting this I can adjust the trigger point. And what I'm looking for is a nice square wave, so that when there's a noise, when there's sound, it's going to create the peak. And because I'm comparing 2 filtered sound levels, this would work even in a noisy environment, which was kind of what I'm looking for, as long as there weren't too many sort of sudden noises coming along. but background noise, there's a continuous hum or just noise of any source, and it's at a constant level, that creates the baseline, which is the slower moving average. So it can adapt this way. This would adapt to ambient noise levels to some extent. You know, that's the theory anyway. So what I'm going to do is I've wired up the buffer circuit on the fast average. I've tested the output on here. What you're seeing here, this you can see that the this is changing according to my voice because this is picking up noise. Look at that. So after I did that, it was like it was upset, generating more noise. I don't know. But the point here for the application that I want to make this for, it would need to be able to hear a clatter like that, because if I take the controller the whole point with this is to be able to smash the button on the controller. You can see various bits of noise, and so I might need to add some filtering to get rid of very low frequency noise, because just breathing on the thing is very sensitive right now. But anyway, so this is going to need to be tuned, but yeah, you can see a peak. I mean, it's picking up the noise, but obviously I've got to tune this or get the circuit to work, so that's really sensitive for the case that's required here. I'm going to have to filter out low frequencies for sure. But when you hit the button, it knows when you hit the button because it can hear it. This avoids having to figure out how to electrically wire the button of a controller in order to measure lag. Right? It's just, and that works. That's good enough as long as you have it close, right? Not trying to do it from. If you go and do it, if you're a meter away, it would be 3 milliseconds. So you want to be close. The accuracy of this only needs to be to within a millisecond is absolutely fine. So I think it's more than good enough. But anyway, so with this control, the output goes into a second operational amplifier. So let's just wire that up. Second operational amplifier, positive input. The second operational amplifier, negative input, it comes from the slow filter. And we're almost there, and then I can just take the scope input and connect it to the output of the second operational amplifier. Now nothing is happening, so to understand why, I need to see more traces. In fact, 3 traces here is good. So this is a 4-channel scope. This is why you want multi-channel scopes, because what I have is I want to look at the signal from the 2 filters, and I want to look at the output of the final op-amp, which is doing the comparison between the 2 filters. So let's go and do this. This is where I wish I had the color codes on these. They're all red right now, so it makes it but this is channel 1. So channel 1 is going to the, turn on channel 1, turn off channel 2 for now. On channel 1, we have the slow filter. You can see it working. There's a great deal of sensitivity here though, which is slightly so actually it's just picking up a lot of ambient noise. The second second channel is going to be the fast filter, which is here. Look at the voltage there. So now we have a comparison between fast filter and the slow filter. You can see it responding to my voice. I'm going to just increase the amplitude. Hello? Okay, yeah, you can see that quite nicely. I might try increasing the amplitude a bit more. Just bring the offsets down. Where's the... Right, so this one is the fast. Here's the slow. Hello? Yeah, you can see a big difference between them. Hello. So the yellow one is the slow, and the blue one is the fast. Now if I clap, the behavior seems incorrect, so I need to figure this out a little bit. Where has it gone wrong? What's confusing me a little bit is that the rise time is not... Oh, it's sensitive to the... Ha ha ha. It doesn't... Yeah, it's not quite working right, because what I would expect to see is that the it takes longer to rise on the slow one, but I'm not seeing that for some reason. Right. I know, I thought sure I saw it before, but now I don't. So I have to debug that. See, I've just stopped it there. They're both rising at the same time. Now the way I fixed that, I had that before, but the way I fixed that was to use a charging resistor. No, this isn't going to work. What should happen is that when the sound hits, the slow filter rises more slowly. 1004 rising more slowly. It doesn't rise more slowly. Why doesn't it rise more slowly? Bum, 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 bum. It might be because I need a bigger resistance. Let's make them even. The discharge and charge resistors, you can make them both. You can make them both 10k. That's a 10k resistor. Let's try this. This is on the slow circuit. I'm just modifying the slow circuit to put a 10k resistor instead of 1k resistor, charging the circuit, charging the capacitor. When there is a transient pulse, it should take longer for it to follow. Let's try. Seem to have lost track of my... Oh, there it is. No? Hello? We have the two. And because it's divided down, I'm going to have to make it the same on both. Let's find another 10k resistor. That way, there's one. To reuse ones while I was getting them out of the... So, charging resistor of 10k, discharging resistor of 10k. On both circuits, the only difference now is the capacitor. There's a great sensitivity on the blue one compared to the Alright, the scales are different between the two traces, so let's make the scale of them the same, and then I'm going to have an offset, so I have to sort of shift the... There it is. Another bug. There we go. La 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 la. Okay, so that's a very nice signal on the top. The bottom one, not so nice signal. But now I'm wondering whether it's... Well, there's a simple test I can do. Is what if the two circuits should be identical. So the easiest way to verify that is I swap over the capacitors, and then we can see if swapping over the capacitors swaps over the behavior. That's quite a lot of noise there. Hello? Yeah, I'm not convinced that this is operating properly at the moment. I need to check the resistor values because something's gone wrong. Yeah, that's correct. I don't know. That's kind of weird. They're on the same scale. What about the DC off? Well, let's center them both, and reduce the sensitivity of both scales. Yeah, I'm only seeing one. Let's bring it down to the bottom here. Oh, I'm not understanding why. I only see one trace. How is that possible? Let me turn off trace 2. What happened to trace 1? Yeah, that was the slow, but should now be the fast because I put the fast capacitor on there. Smaller capacitor. There's no sign of it. I seem to have lost that trace. Oh, wait a minute, it's turned off. Okay. Right, so it's 1 volt per digit, and per digit per grid per square, and so this is a 1 volt signal. I think there is some sensitivity to the microphone, but it's very poor. If I remove the capacitor, then there's no filtering, and then you can actually see the audio signal, which is approximately, it's 1 volt oscillating, or is moving around 1 volt, offset of 1 volt plus or minus 1 volt. So what I'm going to do to remove any confusion is I'm just going to study this with one input channel for now, which I think is this one. There we go. Press probe number 1. Probe number 1. Probe. Alright, so when I touch the probe, then I'm getting a mains hum signal. Let's, with the capacitors out, I'll check the behavior of both circuits. They should be identical. This one, I have a 2 volt. It's a 2 volt signal, and well, it looks like double the amplitude. That's a bit suspicious. Yeah, they're not the same. So, but the circuit should be the same, so I need to debug that. One thing I've got is the output of the circuits are going, or one of them anyway, was going into the operational amplifier. So I'm just removing that and see if there's, shouldn't make any difference, but you know, we'll test that idea. So this is, I've got a 2 volt offset, and then it is plus or minus 2 volts on the audio frequency, on the audio signal, and then if I put this in here, I've still got a difference. That's half. Are the scales? No, I'm using the same probe to make sure that there's no possible confusion. There's no doubt about it, they're behaving differently. Why? You know, usually that would be a different value resistor. They both come out of the same. Could be a different diode. Could be a different diode. Yes, right. Let's see what happens if, which one am I measuring right now? So I didn't look carefully at which diode that was. This is a 2-volt offset. If I unplug that, its thing goes away. I take my other diode and I put it in. And this is also the same. So the diodes are not the reason for the difference. So let's have a look carefully at the circuit then. If I go and put one of these resistors has to be different. I mean, I can see in here I have from the diode, it goes through a 10k resistor, and then from a 10k resistor to ground. I'm reading the voltage from the tap between the two 10k resistors, which should halve the voltage. This is about right because in the end I'm on a 5-volt supply. So, that interestingly, that 1 volt, 1, 2, 3, 4. This is the bigger one. This doesn't make sense. I think one of these resistors is not what it says, what I think it is. It might be a problem between red and orange, which is never easy to see the difference between red and orange. It's a 10 times difference in the resistance. So I'm going to try measuring these resistors. Let's take that one. What have we got here? Yeah, that's about a 10k resistor. Confirmed. 10k resistor. What else can it be? It has to be the value of the resistors. This one. Oh! This is a short. This is a bad resistor. What do you... Inconceivable. If I look at that. It's wavering around all over the place. I've never seen such a thing. A bad resistor. Brown, black, black, red. And a resistor that has a lower value than it should. Come on, this is not possible. I don't know where these resistors came from. They were part of that pack of stuff. Look at this. It's bizarre. No. That's a 10k. And the colour bands are brown, black, black, red, brown. You can see. You can't really see it, but brown, black, black, red, brown. And then, so I take that off and I take this other one. This one. It's like the current value is currently measuring around 250 ohms. Brown, black, black, red, brown. I mean, unless it was brown, red, black, because this is the one that is ambiguous which way around you read it. I suppose if it was, if it was brown, red, black, black, that would be 120 ohms. That's not what I'm reading. That's quite bizarre, but that would explain why the two were completely different. I've never seen a resistor do that before. I mean, resistors usually fail open circuit. They usually increase their resistance. They don't often reduce their resistance. So is this the same one? Brown, black, black, red. Because the brown, black, black, red, brown is 1, black, black is 0, 0. So that's 1, 0, 0. Red is 2 zeros on the end, so it's 1, 0, 0, 0, 0, which is 10k. And then the brown at the end is the tolerance. It's like how accurate the resistor is. If you read it the other way, you end up with brown, red, black, black. Brown, red, black, black is 1, 2, 0 with no extra zeros, or 120 ohms. Tolerance of the brown band. They used to make these things in such a way that there was no ambiguity, right? Before they added the band. I mean, it's just crazy. They've made it. How do you know which one? One of life's mysteries. Anyway, let's have a look. Yeah, this is a 10k resistor. I'm going to measure all of these 10ks here because, wow, that's crazy. That's 10k. And measure this one. Well, it'll be worn now. I have to measure my resistors. These are all 10k. The thing is that resistor that was like 250 ohms, it's not correct either way. I mean, you know, it'd have to be 120 ohms. How strange. Well, that would explain why the signal was different. So this is checking it with a 10k and going in, but there is no divider. I mean, there's no resistor pulling it to ground. If I add the resistor that pulls it to ground, now we're halving the voltage, and so that's now correct. And we should have this on both sides. So let me set this up on both sides then. So we put the 10k, and then we'll get this and put this 10k in. So there's the divider there. Well, we can turn on the second trace. Which is this blue trace. This one is going to go. Right, so the blue one is now the slow. But the capacitors are out, so they should behave the same, and they are. We can see there. I'll just offset one of these a bit. They are behaving the same, so that's encouraging. Because it's just the duplicate circuit, but now we'll insert the capacitors back in. So starting with the 100 microfarad capacitor on the slow filter, and we can see that that was doing its job, although actually the whole signal has just disappeared for some reason. Oh, right. No, it's still there. Maybe that capacitor's too big. We'll try adding a capacitor onto the fast circuit. La la la. This is capacitor. Because of the fact that I have increased the resistance to 10k, or the one feeding the capacitor, it's actually having the effect of reducing the sensitivity. This may or may not be a problem. La. You can see them rising, but what I'll have to do is let's center both of them. We can see they're about the same, almost the same voltage. We'll switch to, oh, they're not on the same scale. That's weird. How can they not be on the same scale? I don't understand. They should be the same scale. Right, now they're the same scale, but the blue one, which is channel 2, is virtually 0. They're not the same anymore. So what am I missing? They're centered. So the blue one is the large capacitor, and that not doing anything. I've just removed the, so something's bad connection. Has to be. Let's remove the two capacitors, and now they're not behaving the same at all, are they? So what happened there? Hello? Yeah, bad connections, something. I've got a ghost in this machine. How extraordinary. Okay, so back step backwards. Let's verify by comparing on the yellow trace. If I put this in here, oh look, the yellow trace is fine on either. Oh dear, I'm suspecting it's a scope problem, or it could be that the blue trace is on DC mode. AC mode, AC coupling. Oh, they're both on DC coupling. Alright, this is channel 2. The blue one is channel 2. I already checked channel 1 on the slow circuit and it was fine. Really doesn't, maybe it's because I need to connect up the negative. I thought that they were all shared, but maybe not. Yeah. This looks like a bug in the scope, so what I'm going to do is switch back to default. Turn on both traces. Are they on different probe settings? Maybe one is on 10 times and the other isn't. I forgot to check that. Yep. That'll do it. These leads scope probes have sort of setting to divide down the input voltage. So the two scope probes are not set to 10 times, and that's why. Okay, there's that one. That's debugged. But you notice there was multiple bugs. I mean, it was like we had a bad a bad resistor. I think it's potentially possible that the two were cancelling each other out, strangely. So that's why I didn't notice before. That's really perverse. Let's use auto scale and see what happens. No, that's okay. And then we can take this and bring this down. There we are. They are in fact working in exactly the same way right now, which is fine. Now I'm going to reduce the time base. Let's go and do utility acquire display mode roll. Hello? Okay, right, now I think we're cooking because it's beginning to make sense. Try again. I'm going to take my 100 microfarad capacitor and put it on the slow filter section. So now the blue trace is filtered. It doesn't seem to... Well, yeah, the capacitor is also attenuating the signal. Now I can take the smaller capacitor, 10 microfarad capacitor, and put that into the... Oh, and that didn't work. Why? What's wrong? No, I'm putting it in the wrong place. Right, that needs to come here like that. And that is not actually working either. What have I got? Just check. This one. That's the yellow one. Okay. I was putting that in the wrong place. That needs to go here, right? As the diode came out. Let's just reset, because what the hell happened there? Alright. Do we have them at the same level? Okay, here we go again. I'm going to reset the vertical position of the two traces, and then we actually see there's a disagreement again between the two. Why now? Another disagreement between the two. I've taken the capacitors out. There's quite a big difference between the two traces. From the diode to a 10k resistor to ground. From the diode to a 10k resistor to ground. Right, well, let's try swapping the leads. I guess this is getting crazy. It's like this circuit keeps changing its mind all the time, you know. So this way around, the blue one is on the high trace, channel 2, the yellow one is the low trace. The blue is the high one. The blue is the high one. This is right. This is very irritating. I swapped the two cables and it didn't swap them, which means that the issue that we have here Oh, I'm being an idiot. I thought I'd set. So that's the problem. There's so many different things. What it is that the blue is on a more sensitive range. It's the obvious answer. Let's set them both to 100 millivolts. Now they agree. Ugh. Okay. So what's interesting is 100 millivolts, really? Is it that a smaller signal? I don't have the capacitors in at the moment, so now that doesn't make sense. So what I'm going to do is put this to 1 volt per thing, and let's look at the voltage before we go into the divider. There's nothing there. Hello? I think it's all my readings of what was going on have all got disturbed by the problem of the mismatch probes and the resistor. So everything I set before, I was looking at voltages that were actually not correct. So the signal is already smaller than I'd anticipated. So, okay, let's go to 100 millivolts per division, which is what I've got there. And the two are agreeing with each other. At 100 millivolts per division, we're getting a small signal coming out of the input amplifier. The only thing that puzzles me about this is that what we had coming through the amplifier used to be big enough to drive an LED. Well, at 100 millivolts, it's not going to be big enough to drive an LED, so now I don't understand why. If I take, that was the yellow one, off, and I put it just on the output of the diode, I can see that we've gone to, okay, right, it's because the probe is on 10 times. It's not 100 millivolts per division, it's 1 volt per division because the scope probe is at 10 times. Thank you. Right, now that's where the confusion was. I had it, one of the probes was not on 10 times. It's a good idea to keep them on 10 times, apparently. So this is 1 volt per division. Okay, and they are in agreement with each other. Okay, and we're going to take the bigger of the two capacitors and put it in circuit on the sort of averaging filter. And we get some crazy stuff going on. That's the right way round. What's that? What's all that noise? That's crazy. That was a lot of noise generated there, wasn't it? Now, see, the weird thing is it's generating noise on the other circuit, so it must be a bad connection. Come on, people. It had to be a bad connection because it wasn't even working in that circuit. So I'm going to turn off the blue trace for a moment. So no, turn off the blue trace for a moment. I should have the yellow trace. Let's just work on the yellow circuit. If I take off this capacitor, I've got this sort of dancing around going on. Hello? I think it was a bad connection, but anyway, look, that is working. Okay, that's good. Now we put in the filter capacitor. Hello? It's not changing the DC voltage, which is still 1 volt, but it's greatly attenuating the signal because the filter capacitor is in itself filtering the audio signal. Now if I sing into it a bit, you can see I can actually raise the level of the voltage up, but it requires a pretty big time for that. So maybe that capacitor is just too big. We're going to try a 10 microfarad capacitor in here and see how this behaves. Hello? That's moving, but again it's very slow. But in part that could be because I've got a 10 kilo ohm resistor, whereas before it was only 1k. But I had all these other issues that were confusing things. So what I'm going to do is take out those 10k's and put back 1k's, because I was basically in La La Land for a while. So we're going to have the charging resistor is 1k and the discharging resistor is 10k. Looking for a 10k resistor, 1k resistor, here it is, 1k. Alright, so then we come back to this and onto there. 1k charging resistor, 10k discharging resistor on a 10 microfarad capacitor. It is responding to my voice and I get a nice little peak. That's fine. If I put in a 100 microfarad capacitor, I also get a peak, but it's less of a peak. And that was to be expected. It would be, the bigger capacitor is probably going to be, well, it is going to be doing more filtering. So it's going to be quieter. Let's turn on both traces. They are actually in agreement. Look at that. There's. I turned it off. There we are. They're actually on top of each other, and we can see that there is a difference between them. So that's encouraging. If I clap, yeah, it's working now. So I think it was working. It was just that my measurements were all over the place. Oh, and plus the resistor. But this is actually what I was looking for. So what we do is I'm going to increase the sensitivity of both traces and sort of move them down so that, say that there is going to be 0 volts. So now you can see I've got 2 traces. I'm going to just do a nice big loud one and then stop. Perfect. This is what I was looking for. The yellow one is the one with the bigger capacitor. It takes longer to rise up. Does it? Actually, it doesn't really. I mean, okay, yes, it does. It gets there, but that's because the amplitude is greater. I tell you what, if I increase the amplitude of the yellow one, then it's going to have to adjust the offset there. The question is, does it reach the peak? Oh yeah, that's fine. It does. The point is, does it reach the peak later? And it does. There is actually a time differential. This is what I was hoping, that not just that it would be lower amplitude, but that the yellow one would reach a peak a little bit after the blue one. So the point here then is that, you know, once the thing is balanced, because I may need to compensate for the fact that the bigger capacitor sort of attenuates the signal. But if it was balanced so that the two then are similar amplitude, you can see that for a certain amount of time, the blue is ahead of the yellow. And that would generate, if that is when the signal goes on, it would be on only from there to about there. So it would be a little spike that would occur, which is the behavior I'm looking for. That obviously only works if there is a time delay on the slower average. What happens afterwards is of less interest. So I think that looks okay, but what I need to do now is get the third probe going. Oh, that's tragic. Oh dear me. My box of loose components have just gone everywhere. All over the floor. How annoying. They're not worth very much. I mean, probably this total that just fell on the floor might be worth a pound. They make a mess. I'm just clearing up the obvious bits. Oh boy, okay, right. So, that bit done, I want to measure the input into the final operational amplifier so this is one of the inputs into the operational amplifier, and then this is the input into the other operational amplifier. Let's just, hello. Okay, well I've got a blue signal which seems to be working fine. Now what's happened to the yellow one? There's the yellow one. So again, now we've got complete disagreement between the two, which is quite annoying. The input into so I've got the wrong, what's the wrong connection? So let's try that. This is a bit better. Whoa. This is the blue one. This is the yellow one. So they're behaving the same on both. I think something has happened with the oh, come on. Let's just leave them like that for the minute. So this is the yellow one. It's doing nothing that makes any sense. This one, hello? Nothing is really making any sense at all of a sudden. So let's go and take a, let's just remove some bits here. So this thing, I don't know what that is. These are the two power supplies. That's that voltage divider, but I will need eventually. That's the output of the voltage divider. This is the feedback of the buffer. Let's start with that. So the fast filter. I need to take the output of the fast filter, which is this one, and put it into the op-amp buffer circuit. Take this yellow one, turn off the blue trace. So we're just using the yellow trace right now. That one is going to go in to the output of the buffer circuit. 100 millivolts per division. We should have, yeah, it's able to pick up the microphone noise. Hello. It's filtered and buffered, and if that line there is 0 volts, it looks like we're just under 2 volts, and that is fine. Right, good. Now the output of this buffer should now go to a variable resistor acting as a voltage divider. So now if I take this one, plug it into op-amp input, but that, see if it settles down. Okay, that one should now be adjustable from 0 volts to 2 volts. So that's working. That's adjustable. So great. And it's picking things up. So cool. The next one that we want is to go from the slow buffer circuit, the slow filter rather, and put it into the other op-amp input, and I'm going to connect the second second trace to that second op-amp input, which is the blue trace now. Oh, at last something seems to be working. You can see, yeah, you can see that the blue trace lags behind the yellow trace just a little bit. Right, so that's fine. Now, the interesting thing is these need to be calibrated to be right at the same voltage, because the final stage is the op-amp that checks which voltage is higher, which is what I want to check. So let's just calibrate that there and this there, so they're right on top of each other. We can already see that currently the blue trace, which is the one from the, is that the fast one? No, the yellow one is the fast one. That's the yellow one. Yes, the yellow one is the fast one. That's already low in voltage. So I don't understand. Now this is the next puzzling point. Why is the baseline of the blue trace? Okay, because the scale of the two traces is incorrect. They're not the same. All right, now they're the same. Yay! All right, so now I can adjust the two to put them right on top of each other. That little peak that you saw there was due to somebody across the road closing the door. It was louder than me tapping this. It's like these microphones are weird because they pick things up. Sometimes it seems like with them they're really sensitive to things off in the distance. It's really strange. This is looking promising. So what I'm going to do is increase the scale 5 times. And now, because it's a DC signal, I have to come on, where are you? Oh, scope. Honestly. Right. So I want the offsets to be the same for both. I have them at minus 200 millivolts. There we go. That's really nice. Look at that. I'm just going to do it with talking. Hello. And you can see immediately, as soon as I said hello, the yellow one. It also has admittedly, it's louder than the blue one. So it's almost like that's that compensation. If I really want to get this to work exactly as intended, the blue one needs to be scaled up. Or the yellow one scaled down. The problem is that there's also an offset, you see. So if I have it so that the DC levels are the same. But I suspect for my use case here, that will probably be good enough for now. Oh, it's weird that I have to turn this thing all the way to maximum. So I may have to introduce an offset circuit to make this work even better, but I think it's actually close enough for a first pass of the theory. What I'm going to do now is to take a third. It's time for a third trace. This is the red trace. Don't know if there's a way of changing the colour. It's the green. Green is probably easier to see. So I'll use the 4th channel. Put this on the 4th channel. I'll be happy if basically the circuit is working as intended. How good it is for the use case, that's another question. Is it at least working? I take that and put it in the output of the operational amplifier. I'm just going to turn off the other 2 traces a minute, just leave us with this green one. Now, as you can see, it is actually square waves again. I need to increase the amplitude of this. I can move this down. Now, it's triggering even when there isn't much of a noise. What will happen if I... Hello? Aha! And there it is. The theory works. Look at that. Now, do you notice I was just making some noise and then I do the clap. This is the test. It didn't work that time. La, la. That's working. So obviously I need to tweak it And now I can already see that there's something slightly off, but it's still able to detect a sudden noise when there's noise, which was the whole point. Now, this also acts as a sensitivity thing, so let's see if I... Here we go. Boo! Yo. Hello. Got a new audio sensor. So it will only get better as I refine it a little bit, but let's see. This is the real test, is to get that controller. Where did I put it? The controller. I think we'll call that a success. Look at that. I don't even have to hit it that hard. Well, there you go. That was good fun. The first proper test of my oscilloscope. So, right, that's another project started. Very happy with that. I think to make this, notice how it's not even changing to my voice. It's sort of like, is it? Because it's, maybe sometimes, they're sort of adapting more or less to the ambient. What it's sensitive to are sudden loud noises. But anyway, what I would need to do to continue this project is figure out this audio trigger circuit. Then I need to do a similar thing for a video circuit. That might actually be able to be the same, which would be kind of cool. The same kind of circuit where it looks at the light level on the screen and detects a sudden change in the light level. But the other alternative is, if it needs to be more intelligent, is that one could be fed into an analog input on a microcontroller, and then I can run an algorithm on the actual waveform. Admittedly, that could also be done on the audio circuit. That would require 2 analog inputs. And but anyway, I wanted to see if, staying in the analog domain and also improve my knowledge and expertise. Thanks for watching. I will be back later after my evening break. We're watching Battlestar Galactica. Yes, it's a fantastic series. I'll be back later to do some software. And also, don't forget, at midnight tonight, there is a minor single release. It's the remix of Hummin'. And, hey, Mark! How you doing? Did you just arrive? You're always arriving just as I'm leaving. I'll be back, though. I'll be back later, because at midnight there's the release anyway. And I'm not sure what I'll work on yet, but I'll decide. But in the meantime, from me and my smoke, me and my scope, I bid you good evening. Yes. Take care, everyone. Oh, okay. Okay, but I'll catch you later. I'm not on my computer here. I'm on my Surface Pro, so nothing's set up for the others. Still trying to figure out what's going on. Oh, all right. Let me give you a quick recap then. Okay, so what's going on is I want to make a device inspired by what I did here, which was to have a microcontroller that could drive an 8-digit display here. So the microcontroller is only an 8-bit chip. The rest of this was the drivers for the display. But to have a microcontroller in a box with a 4-digit display like this, and then have 2 electronic circuits attached to it, or sensors attached to it. One is an audio sensor, the other one is a light sensor. So I've just been working on the audio sensor. You can see down here that when there are sudden noises, you get a very nice peak here. So a microcontroller would be able to detect a noise using a circuit like this. The second input is going to be through a light sensitive detector of some kind, to be decided. And so that light sensitive detector, the idea is you take that and stick it on your screen, and it's connected via a cable to the box that has the display on it. In the box there is also a microphone. The microphone in place, and then the box. Oh, I got tangled up here. You place next to a game controller. When you smash the game controller button, let me try it. Hang on, it's a bit noisy there. It can detect. Yeah, it's become a bit more sensitive. When it's right, it will detect that the button was hit. So the microcontroller knows the precise time that the button was pressed. It's then looking at the sensor that you've sort of attached to your TV screen via, with a little bit of blue tack or whatever, is able to look at the pixels on the screen. And when it sees a change, it knows that the whole path from pressing a button on your controller to it changing something in the game has been completed, and it would time that and display it in milliseconds on a thing. So in this way you can time the lag not only of your monitor but of an actual video game, so that you know you can find out what how many frames of lag a particular video game has. And I really want to have this device. I know there are testers for this, but what I want to do is also test not just the lag time of your monitor, but the lag time of the whole pathway, all the way through. Press the button, the electronics in here has to process the button press, has to go through the cable, has to be picked up by the hardware in the console, has to be read by the engine in the console, has to be fed in to the rendering that's happening in the other buffer, in double buffering, has to be processed through perhaps multi-threaded rendering that really slows everything down until eventually whatever you did causes something to change on the screen. You stick it anywhere where it would change, hit the button, and you know the whole pathway. Controller, input, the USB or whichever system it uses, input, reading it into the game, re-rendering everything, taking the video output, firing it out through the HDMI, it going into your monitor where another computer in effect is all stacks of computers in effect. It goes in, it gets processed, and it gets sent to the panel of the display until eventually you see it. The whole lot. Because that time has got crazy. And it's an extension of an idea that I first implemented in Kickoff Revival, where I did it in a different way, but it's still pretty much the same. Just I basically had a device that was on the screen and made a tone depending on whether it was bright or dark. And I took a microphone, recorded the sound of me hitting the controller, and then the sound that changed when things changed on the screen, and then you look at the waveform in Audacity and you get a very accurate reading of the time between one and the other. This was before I really could use a high-speed camera. They're more sort of easy to get now. Yes, and it was like 1/10 of a second and freaked me out. And so I figured out a way of cutting that in half. But that's what I want, because I think it's important that this is a piece of information that is actually used by reviewers, frankly, because they never really go into this kind of thing. But it should be a specification that's more important, in my opinion, than some of the others, such as how many megabytes or gigabytes, I should say, what the screen resolution is. Is it 4K or is it just HD? And so on and so forth. But nobody ever provides figures for the most important thing for interaction, which is responsiveness, which is a low latency. And I want to make a box that does that. And then I can know which games out there did. Other purposes too. It's very specific. I don't think there's other purposes. It's very specific, I think, to this. But it's more than just games. You can get for example, on your computer, it's kind of important, I think, that when you type, it comes up immediately. So I'm using a Surface Pro here. Did you know that the Surface Pro has a 50 millisecond lag between the video hardware and the screen? I had a video up on YouTube where I was showing this. 50 milliseconds. That's 4 frames. 3 frames delay for your video signal to transmit itself 6 inches. You can, in that time, you can transmit a video signal all the way from the UK to New York and back again. Yeah, it could. Yes, or it could be. You could also potentially use it as a reaction timer. And so on. Yeah. But anyway, there we go. But this bit that I've done here is just an experiment on the audio, hooking up an audio circuit. And it's very sensitive right now, but just reduce the sensitivity. This uses a audio amplifier IC to take the signal from here, that's picked up by the microphone, and then passes it through 2 detection stages with filter capacitors that work at different times. One's 100 microfarad, the other's 10, so that one rises more quickly than the other, and then from there it's possible to create these pulses. See, look, if I suddenly start singing, it will detect it, and then it recalibrates itself so that it loses interest until it hears another peak. It takes a little bit for it to. So it's a little more clever than just being, oh, there's a noise, light and LED. This is like comparing a transient noise to the background level of the noise. Anyway, that's it. So I'll be back later. Thanks for watching. Great to see you, Mark. I'll play your theme later on. And as I said, midnight tonight, they've got the release of the remixed version of Hummin', where it's actually properly mixed, whereas the first one was really just a scratch track. I think it came out quite well, but we'll see. See what you think. Take care, everybody. I'll catch you later. Bye.